Did recently with my student Netta Engelhardt. But first, I want to wish David a very happy birthday. When David was being recruited to become director of the KITP in Santa Barbara, the director at the time was Jim Hartle. And Jim didn't trust the UCSB administration. He thought they were going to screw up the appointment. So before David arrived for his campus visit, Jim met with every administrator that David was going to meet, up to and including the chancellor, and coached them on what they should say and what they shouldn't say. He even convinced the chancellor to fly out to Princeton and meet with David personally to help convince him to come. Now, David's appointment had to be approved by the physics department at UCSB also. And when the time came, there was, of course, great enthusiasm for someone of David's stature to join our department, but there was also some reservation about David's strong personality. You see, UCSB always had a very congenial physics department. We all sort of got along, and and it was expressed, well, maybe David would disrupt this atmosphere. In the end, of course, we all approved David's appointment unanimously, but I have to say, he has livened up a number of our department meetings. On a more personal note, I have to say having David as a colleague has been a real inspiration. Time and time again, David seems to ask the most perceptive question in seminars, showing that he really understands everything much better than anyone else in the room. And this isn't just about quantum field theory seminars. On a variety of topics, David seems to be up and knows everything. Anyway, it's been a great pleasure having you as a colleague. Happy birthday. Okay, so a powerful feature of this gauge gravity duality is that statements that are easy to establish on one side are often highly non-trivial results about the dual theory. In fact, the results in the dual theory are often very difficult, if not impossible, to establish directly. But we can argue, given our confidence in this duality, that they must be true nevertheless. An early example is the fact that black hole formation and evaporation must be a unitary process, because it follows simply from the unitary evolution in the dual field theory. So what I want to do today is to discuss some new results along these same lines. Statements about quantum gravity that follow from very simple properties of the dual field theory. And I'm going to give arguments which I find convincing, but they are certainly not proofs, and I will show you. They are based on a few assumptions. So the first assumption I'm going to make is that gauge gravity duality holds in a strong form. The two theories are equivalent at finite n and finite coupling. Second assumption is that if a space-time has several asymptotic regions, then each region is dual to a separate copy of the gauge theory. States, of course, can be entangled between the two Hilbert spaces, but there's no direct coupling between these field theories. This is, in fact, a standard assumption which has been made in gauge gravity duality so far. Finally, I'm going to assume that the dual theory describes the entire space-time, even including the region inside black holes. There's been some debate about this recently, especially since the firewall paper came out, and I'll comment at the end about what happens if you relax it. But for the moment, let's just assume the gauge theory can describe everything. Okay, so I'm going to start with a very simple question. When can two quantum field theories communicate with each other? So, an obvious answer is that if the two quantum field theories live on separate spacetimes, they can't send signals to each other. So these diamonds are supposed to represent Minkowski space, conformally compactified so that future and past null infinity are attached, just like Andy was describing this morning. And it's obvious, it seems, that if you have quantum field theories on separate spacetimes, they can't communicate, because how can you send a signal across a region where there's no spacetime? Now, if these quantum field theories are conformally invariant, there's actually a subtlety. Given two copies, my goodness, these pictures are not coming out. I apologize, I don't know what's going on. Anyway, so let me describe what's supposed to be represented here. This is supposed to be a static cylinder Okay, just the product of a sphere across time. And over here I have two static cylinders. And I'm considering now two copies of a conformal field theory, say in its ground state, on Minkowski space. And one can imagine that those two copies of the field theory are conformally mapped into one static cylinder, such as the case on the left, or two separate static cylinders, such as the case on the right. In the first case, these two conformal field theories are actually subsets of a larger conformal field theory living on the entire static cylinder. And it's obvious that you could send signals from CFT1 to CFT2 in this case. But in the right, you can't. These are now, again, theories on disconnected spacetimes, and you can't communicate. And you can't tell, just by looking at one of the copies of the conformal field theory, whether it can communicate with another or not. It can only be detected by some, well, correlation function or something non-local involving the two CFTs. So in this case, you have signals from one conformal field theory to the other. Another example is de Sitter space. De Sitter space is, of course, the space with this hyperboloid. When you conformally map that to a static cylinder, you have to multiply the metric by a conformal factor which goes to 0, so the infinite size spheres get mapped to a finite size. That maps the infinite time in de Sitter space to a finite time. So de Sitter space is conformally mapped to just a finite piece of a static cylinder, and therefore, in principle, you can have a conformal field theory on de Sitter space, a conformal field theory on Minkowski space, and they could communicate if they were both conformally mapped into the same Einstein static universe, or this static cylinder. Okay, so when can two field theories communicate? I'll just say that two field theories are independent if the joint Hilbert space of the system can be written as a simple tensor product, and all the operators take the form of an operator acting on one Hilbert space across the identity on the other. So these are operators in the first theory, operators in the second theory, and in that case, they can't communicate. Sure. Okay. But that's not going to help you send signals. So, okay. So I guess you're right. All operators are not of that form. Okay. Fair. Good point. Okay. So this is what we just call a no transmission principle. It's simply the obvious statement that if you have two independent quantum field theories, they can't send signals to each other. Okay. It sounds trivial. But now I claim it has implications in the context of holography for quantum gravity. Because if two independent quantum field theories have gravity duals, then no signals can be transmitted between their bulk duals. So that has a number of consequences, and let's start to explore it. So the first one is that you cannot send signals through a black hole singularity. So let's consider the standard sort of eternal black hole, a sort of Schwarzschild ADS solution with the two asymptotic regions and the future and past singularity. And I'm just going to take another copy of that space-time and put it on top. So the black hole singularity of the first one becomes the white hole singularity of the second. The joining point here? There is no joining point. This is an infinite cylinder. That's another infinite cylinder. There's no point there. It's just not part of the boundary. No, you can't. This isn't Minkowski space. I'm sorry, I'm thinking about the global ADS. So in Minkowski space, you also have trouble because it's you have a uniform energy density over the Minkowski space. If you try to map it to an Einstein static universe, you get singularities, and then you can't communicate from one. If you're at finite temperature, one Minkowski patch doesn't communicate with another. But a simpler example, the one I wanted to consider here, is global ADS. So the boundary is still an infinite cylinder, S3 cross R, and it's simply an artifact of the Penrose rescaling that it looks finite. This is infinite proper time in both directions. And so there's no point here. This is just a complete CFT. That's another one. They're independent. And you can ask, could quantum gravity somehow resolve this singularity to allow signals from the past to evolve into the future? And I claim the answer is obviously no. These CFTs are independent, and you cannot transmit signals through this singularity. The fact that there's another, yes, Andy? We're getting to that in 1 second. Just hold that question for one slide. The fact that there's another asymptotic region here with its own copy of the CFT is really not relevant for this argument. You can in fact think of the CFT1 as including both copies, both asymptotic regions here, or you could just imagine a black hole formed from collapse with one asymptotic region and flip it around and get the same conclusion. You can make up a rule. I'll discuss this later. You can make up a rule which would, arbitrarily map a state here to a state there. That would violate one of my assumptions, which says that the two theories are completely equivalent. That would be extra input that you're putting into the CFT, which is not there originally. You're making up another rule arbitrarily or something, which would then not be contained in the original. Well, that's what I said. I said there are these two cases, okay. Let me agree that you could make up an arbitrary rule, and I am not going to for the purposes of this argument, I'm going to assume that we don't do that. You could, but I don't like it because first of all, it's arbitrary, and I don't see any reason to get a preferred way to map. And second of all, it seems to me as extra input, which is not part of the regular CFT. Okay, but as Andy said, most black holes are not Schwarzschild. Most black holes have a little rotation. They might even carry charge, and the Penrose diagram doesn't look like this. It looks like that. Okay, so now what's going on? So here we have our two asymptotic regions initially with the event horizon, but if the black hole is rotating or charged, you come in and you don't find a singularity. There's an inner horizon. The singularities are time-like. You can go through it. And then you have other asymptotically ADS regions. And in fact, the diagram repeats infinitely often to the future and past. This seems like a blatant violation of this no transmission principle I just told you about. It seems that you could, in fact, send signals from CFT1 through to CFT2. This just doesn't make sense from a field theory. You have two field theories on separate spacetimes. How can they possibly be communicating? The answer is that the inner horizon is unstable. In the asymptotically flat context, ordinary charged black holes, it's been shown that any perturbation of the black hole will cause the curvature to diverge on the inner horizon. It was thought for a while that it would just turn into a Schwarzschild singularity, but that's not what happens. The singularity, in fact, remains null and is weak in the sense that the metric remains continuous, but the Christoffel symbols are not, the metric is continuous but not differentiable, and the Christoffel symbols are not square integrable, and all that means that you can't evolve Einstein's equation past that point. So in fact, classically, in that case, you cannot send signals through a Reisner-Nordstrom black hole in the asymptotically flat case. Yes? Yes. Yeah, they're now real theorems. In the asymptotically flat case, de Fermos was the first person to prove it, and there have been some subsequent papers. It's all quite, and even in Kerr, right? They have nice results for Kerr now as well. In ADS, the situation is likely to be worse because perturbations outside a black hole in ADS fall off more slowly than they do in asymptotically flat space-time. So although it's not been rigorously shown, the expectation is the singularity on the inner horizon is going to be stronger than this weak null singularity, although we don't really know exactly what it is. So that's a classical argument for why you can't just send signals through. But this no transmission principle says that even in full quantum gravity, even if you allow all quantum gravity effects, you're never going to be able to get through this singularity because it would then violate holography in the sense that you'd be sending signals between these disconnected field theories. So that's one result. Now let me turn to another class of results which apply when this boundary CFT is singular. So what do I mean by that? Some CFTs cannot be evolved past a certain time. And now you're probably wondering, what do I mean by that? Because clearly I can do a conformal transformation and map any finite time to an infinite time. So I'll answer that question and give you a conformally invariant definition in a minute on the next slide. But let me just assume I have a notion of a singular CFT, and then the answer or the conclusion is that if evolution on the boundary stops, then evolution in the bulk must stop. And that means that there must be a cosmological singularity classically. So in the classical limit, the evolution in the bulk must hit a singularity which extends all the way out to infinity, cutting off the spacetime, a real cosmological singularity in the bulk, which quantum gravity cannot resolve into a bounce. Because if it could, then again, you could send signals through the bulk, which would then connect these different independent CFTs. Okay, so what is a singular CFT? So first of all, I'm going to consider conformal field theories on maximally conformally extended spacetimes. What that means is I want to consider spacetime which cannot be conformally mapped as a proper subset into any larger spacetime. Okay, so we're going to start with that. And I'm going to also, for simplicity, assume our spacetime that the CFT lives on is topologically S cross R, where S is compact. If you want to think about Minkowski space, you can do that by conformally mapping to the static cylinder. And I'm also going to assume the metrics that the field theory lives on have a Cauchy surface. And if it has a Cauchy surface, meaning that you can evolve uniquely everywhere in the future and past, then it can actually be foliated by one parameter family of Cauchy surfaces. This is not an extra assumption. It just follows if you have one Cauchy surface, you have this one parameter family. Okay, so now we can define a standard conformal frame to be one in which the volume of these Cauchy surfaces is bounded from above and below by non-zero constants for all t. Okay, and I claim that if evolution stops at finite time in a standard conformal frame, that's a conformally invariant notion. You can't then conformally rescale time to infinity without causing the volumes to become infinite as well. And so the definition is conformal field theory is singular if the evolution ends in finite time in a standard conformal frame. So do such CFTs exist? And of course, I wouldn't be talking about them if I didn't have examples. So here are three classes of examples which have been discussed in the literature for the past decade or so. First, you can put the CFT on any space-time which itself has a cosmological singularity. So I'm talking about the metric on the boundary now, and I'm imagining that it's, well, it could be some sort of cosmological metric like the one here, which is translationally invariant. Nothing depends on x, but clearly time dependent, and there's a singularity at t equal to 0. Now, if the sum of these exponents pi is 1 and the sum of the squares is 1, this is a familiar metric in general relativity called the Kasner metric. But to put this into a standard conformal frame, I want the volume to stay bounded, so I'm going to assume that the sum of the p's is 0. Okay, so the volume stays fixed. You can either compactify these x's to think of them as compact. As I said, I want to consider field theories on a compact space. And yeah, it's probably easier just to think of them as periodically identified. Okay, so this is one class of CFTs which has been discussed. Now, another class is you can destabilize an otherwise well-behaved CFT by adding a potential which is unbounded from below. So, for example, if your CFT is three-dimensional, 2 plus 1 dimensional, and you have a dimension 1 operator O, say a trace of some symmetric product of the scalars in some typical examples, you can add a triple trace term like O cubed, which causes the potential to be unbounded from below, and you find that operators now roll off to infinity in finite time, and the evolution stops. That's been discussed by several people. And finally, you can add a relevant perturbation of the appropriate sign to a CFT on de Sitter space. Now you might say, what's wrong with CFT on de Sitter space? Well, I know Sasha told us this morning that everything is wrong with CFT. But aside from that, you might think that a CFT on de Sitter space, especially perturbed by just a small relevant perturbation, should be okay. But in fact, it's not okay by the definition I just gave, because to map de Sitter space to a static cylinder, you have to multiply the metric by a conformal factor which goes to 0. And what happens is that the coefficient of this relevant perturbation then gets mapped by the conformal factor to a negative power, and it blows up. So it's as if the CFT is being driven by a singular source. I'm not talking about Euclidean. Yes, everything here is fundamentally Lorentzian. I'm interested in evolution. Yes, okay. But I want to mention that Eliezer Rabinovici and Barbon have written several interesting papers on both of these. And I guess you've also written on this one. I just forgot to, very recently on this one also. So Eliezer's contributed to all of this. Milne is included as a special, well, actually not with this case. No, I'm going to talk about Milne in a minute. You'll recognize it. Okay, so here are some examples of singular CFTs. And so now I've claimed that if you have one of these, there has to be a singularity in the bulk. And we can study that at various levels of approximation. So the first level is just the classical GR, or classical supergravity limit. And already that's interesting, because first of all these papers that have discussed this have shown that there are bulk solutions with cosmological singularities. Okay, so if you have a CFT of one of these types and evolution ends at finite time on the boundary, the bulk solution will have a cosmological singularity. But what this no transmission principle tells us is that this must always be the case. There must always be a singularity which not only sort of exists in the asymptotic region, it has to exist all the way through. It can't have any holes in it. And, well, if the boundary metric is a singular cosmology, not one of these other cases, so if it's sort of a type 1 type singular CFT, we get a purely geometric result, which is like a new type of singularity theorem. And this result says that if the conformal boundary metric of an asymptotically anti-de Sitter solution of low-energy string theory has a cosmological singularity, then the bulk solution must also have a cosmological singularity. This is something we can hope to prove directly. I haven't been successful yet in proving it. We tried, but I think it's true, and I think one should be able to prove it using maybe techniques similar to what's been used in other singularity type theorems arguments. It's just a classical result about solutions. It's not obvious, because there are metrics, such as the one I have at the bottom here, which has a singular boundary and a non-singular bulk. Okay, so the metric I wrote down here is a metric for an asymptotically ADS solution. When z is 0, you get exactly the metric I had before for a singular boundary metric. But clearly, when any z is not 0, there's no singularity, and it looks like a regulated form of Kasner where you have a bounce. Now, you can check that this metric violates the null energy condition. Okay, so it's not very physical. It's not going to arise as a solution of any supergravity theory, but it just means that one has to sort of think about what the appropriate energy condition is and how one could show that with that energy condition satisfied, you get a singularity. Okay, that was classical supergravity. Now, what about classical string theory? Let's consider a Lorentzian cone. So this is two-dimensional Minkowski space written in these so-called Milne coordinates, and I'm going to identify x with some periodicity x naught. Okay, so this metric has a conical singularity at tau equal to 0. And now it's known that if you put anti-periodic boundary conditions for fermions around this circle, closed string winding modes become tachyonic when the size of the circle becomes the string scale. So when the magnitude of tau times x naught is the order of the string scale, you develop tachyons. And in a very nice paper by Eva and John McGreevy, they showed that space-time effectively ends when this tachyon condenses. All the modes of the string become very massive, including the graviton, and there's basically no low-energy gravity description at all. But this cone, this Lorentzian cone, consists of two parts. If tau goes from minus infinity to plus infinity, you have a collapsing cone in the past and an expanding cone in the future and some tachyon stuff in the middle. And you can ask, can signals propagate from the past cone to the future cone? And I claim the answer is no. So let's consider a simple case where you take three-dimensional anti-de Sitter space and Poincare coordinates. So here is three-dimensional, here's two-dimensional Minkowski space written in these Milne coordinates. And so this is basically ADS3 with an identification. And again, the tachyons condense. Now when tau times x naught divided by z, the proper size of the circle, becomes less than the string scale. So here's the space-time diagram. We have tau negative in the past, tau positive in the future. There's a singularity at tau equal to 0. And there is a region which was supposed to be shaded, but not coming out. Anyway, there's a region around tau equal to 0 where the tachyon condenses. And you notice that even though the tachyons condense all the way out to infinity, by this condition, as z goes to 0, tau goes to 0. So out near the boundary, the region of tachyon condensation is just collapsing to this tau equal to 0 point. The metric on the boundary is this double cone. And that's where the CFTs lives. So the question of whether signals in the bulk could propagate through the tachyon condensate from the past to the future is the same as whether signals can propagate from this past CFT to the future CFT. But in a standard conformal frame, each light cone is conformal to an infinite cylinder. You can see that just by taking this metric and dividing by tau squared. So you get your standard size circle, and now the proper distance from anything to 0 is infinite. So you now have two copies of a complete CFT on an infinite static cylinder, and they can't possibly communicate with each other, and therefore no signals can propagate through the bulk either. It turns out this metric has another symmetry. It has a boost symmetry in this asymptotic region, and in other coordinates, this is just the BTZ black hole. And the BTZ black hole with its infinite static cylinder is just what you get when you do the conformal transformation of this to the static cylinder. So this is really just another example of my first application where I said you couldn't have transmission from a static black hole to another static black hole through the singularity. If you well, let's see. Well, okay, but I think it works in my favor. If you're going to tell me that mapping to an infinite cylinder causes problems to make the theory on the infinite cylinder, well, okay, I'm not saying the theory has to be the same. I'm saying whatever theory you get, it lives on an infinite cylinder. It'll do what it does. But whatever it does, it can't possibly communicate with the theory living on a completely different infinite cylinder. So I'm not assuming there's no conformal anomalies. I'm not assuming that the theories have to be the same. Well, let's talk about it. I think the diseases will only help my argument. Andy? Yeah. Okay, first of all, the example they were looking at had a null singularity in the bulk. Nadi's here, he can correct me. Hi. Yeah, I think they were looking at an example with a null singularity. Yes. So even in the null case, things were not good for getting bounces. Well, we can, yeah, let me sort of. Okay, so that's the example of sort of classical stringy effects. And now we can go to full quantum gravity. And I've already said that cosmological singularities associated with these singular CFTs will not be resolved, cannot be resolved by quantum gravity. But you might object. You might say, maybe holography just fails because now we have quantum gravity not occurring inside some box, but they're quantum gravity effects near the singularity which are going to extend all the way out to infinity. So maybe that causes the boundary metric to fluctuate. Okay, you could worry about that, and we did. But in the end, everything's okay. So let me tell you why everything's okay. So first of all, we have the result that in Pfefferman-Graham gauge, the boundary metric must be singular for any bulk with large asymptotic curvature, even if the curvature in the bulk is not infinite in the asymptotic region. The reason is simple. If your boundary metric is well behaved, no matter how large the curvature gets, as long as it stays finite, then on any scale smaller than the local curvature scale of the boundary metric will look flat, and the space-time must be asymptotically ADS in that region with the curvature set by the cosmological constant. If you like equations, the answer in terms of equations is that if you just take the leading term in the Pfefferman-Graham expansion with any boundary metric G0, curvature can be large, but as long as it's finite, you discover that the bulk curvature of a metric like that goes to a constant set by the cosmological constant plus z squared times the curvature of G0. So as z goes to 0, the curvature of your boundary metric becomes negligible, and the bulk curvature is always set by the cosmological constant. So anytime you have a bulk metric where the asymptotic curvature is bigger than the scale set by the cosmological constant, the boundary metric must be singular. Now, quantum effects are expected to be significant within a bounded distance to the singularity. So suppose the singularity is at t equal to 0, and quantum effects are important for t less than t0. T0 doesn't have to be the Planck scale. It could be a million Planck scales. It could be anything you want, as long as it's finite. That's the only thing I assume. And then the conformal rescaling, which brings infinity into a finite distance, is going to map this finite time to 0. And so all the quantum gravity effects in the bulk are shrunk to the singular point in the boundary metric. And it doesn't cause the boundary metric to fluctuate, and holography should be applicable. So, and then a sort of a corollary here, any regularization of the CFT on the boundary which allows evolution to continue necessarily removes the cosmological singularity and turns it into a black hole. The singularity just can't continue into the asymptotic region. Okay, just a caveat or a warning. Our conclusion that quantum bounces, that there's no quantum bounces, only applies to these cosmological singularities in holography. There have been lots of papers in the literature talking about bounces due to quantum gravity, and in particular, our results don't rule out bounces based on T-duality, where you go from momentum modes to winding modes when circles get very small, bounces on colliding branes, which I think these cyclic universe models use, or any other approach to quantum gravity, such as loop quantum gravity. Or just stating a result about holography. Oh, okay. A possible holographic bounce. Okay, so I've been assuming that the boundary CFT is singular, and if it's not, if it's singular, then you have these cosmological singularities. You can say, could you have a cosmological singularity in the bulk and not have the CFT singular? And a promising example was discussed by these authors they considered n equals 4 super Yang-Mills on Minkowski space with a time-dependent coupling that vanishes at t equal to 0. And since in the bulk, the square of the Yang-Mills coupling goes like the exponential of the dilaton, if the coupling goes to 0, then the dilaton has to go to minus infinity. That's a bulk field which is going to back react and cause a singularity. So one of the solutions they found is the one given here, which looks like, you know, the ADS and Poincare coordinates, but the metric is now multiplied by t, and it's going to go to 0, getting a singularity at t equals 0, and the dilaton is given there. So you might say, Yang-Mills coupling is going to 0. You can certainly go through that and have a bounce, because then the sort of bulk singularity will get resolved somehow. But in fact, it's not at all obvious that the CFT, the n equals 4 super Yang-Mills, can be evolved past 0 coupling. These authors show that the theory does not become free. The fields become very large, the interactions are always important, and they present strong evidence that the evolution in fact ends because the state becomes singular with infinite energy and infinitely oscillating phases, and they argue that it's likely the evolution just ends. This was not a complete proof because they didn't take all the renormalization effects into account, but it looks, anyway, this is a possible example of a cosmological bounce in holography if it turns out that this theory is thing. Okay, few final comments. You cannot avoid these conclusions by adding couplings between the CFTs. If you just have these two CFTs and you decide to couple them, well, then you could excite one and send signals into the past. It would violate causality. I've already said you could make up a rule, but it's not so good. If the CFT doesn't describe the region inside the horizon, we can't rule out the possibility that quantum gravity allows signals to propagate through a singularity into another region inside the horizon. And if I had 1 more minute, I just want to mention one more application, which is sort of interesting, cosmic censorship. So in general relativity, there is a long-standing conjecture. The long-standing conjecture says that generic asymptotically flat initial data has a maximal evolution that contains a complete null infinity. So that means if you take initial data, which is asymptotically flat, you expect to be able to evolve to a complete space-time which includes all of null infinity. You don't expect naked singularities to just pop out in the past of null infinity. That would cut off evolution and you'd get only a piece of the evolution. Okay, now that's cosmic censorship. It's not been proven yet. That's what everyone expects. But if cosmic censorship fails, it was hoped that quantum gravity would somehow resolve the singularity, or at least provide boundary conditions so evolution would continue. That was a long-standing hope. If naked singularities arise, maybe quantum gravity will take care of them, evolution will continue. Well, I just want to point out that in holography, it's obvious this is true, right? Whatever happens inside the bulk, naked singularities form, no naked singularities, evolution on the boundary now will continue, assuming we don't have these terrible unstable singular CFTs. Normal CFTs, if you can send in something, form a naked singularity, evolution certainly always continues. So in fact, holography does implement this form of cosmic censorship. I'll stop there. Thank you.
They're fully decoupled and you can do it with one ADS.
Two metrics. Okay.
Yeah,
well, I guess.
People work on, I don't know anything about it, but it's called by gravity theory. It's a very real question and requires an ADS because you just get two free fields, for example. One fermion and one scalar. And you would say still there is one preferred energy momentum tensor and then there is another the one difference between the two.
I see.
So you could say symmetric plus some other stringy spin-2 field, and then once you couple them, it will get that.
But I mean, if those fields are coupled in the bulk, then you would have coupling between the two CFTs on the boundary.
The CFTs are truly decoupled, but in the bulk, something more complicated. There's still only one.
I would say that if there's any way to transmit signals from one set of fields to another so that it ends up sending signals from one CFT to the other, it can't.
I mean, they still live only in one, say, three-dimensional space.
Okay.
Integral DPS,
Well, we should talk more about that. That sounds like an interesting example. Oh, you can't get out, right? All I said at the end is that if it doesn't describe the interior, signals could get through the sort of singularity and maybe be inside some other horizon in some future space-time. It can't get out to the asymptotic region. No, you can't get out the white hole.
I didn't understand that question before. If I can discover the different spaces of two CFTs, thereby get something more right or right. You can do that in many different ways, but maybe one specific way has this whole interpretation and the other one is discrete.
Okay, so we thought about that a bit. I mean, first of all, there's really no natural way to do it, because if you have a black hole, you know, your state doesn't settle down. Unless you're in a pure energy eigenstate, the state's going to continue to evolve, and it's just it'll be fluctuations. Anyway, so there's no natural way to do it. Yes, you could pick one. You could avoid these conclusions by saying holography says that when you have these two asymptotic regions, there's some rule that we just haven't found, made up a rule. Okay, so I assume that didn't happen to get this, and it's just sort of clarifying that that's what you're going to have to live with if you want to avoid these conclusions. No, it doesn't. So this is not telling us whether there are classical naked singularities forming an ADS from smooth initial data. It's just directly giving us, it's like black hole evaporation. It's directly giving us sort of the result of the quantum theory that even if naked singularities form, quantum gravity will resolve them. And not only that, I didn't say, but if you can form naked singularities from a standard CFT on a static cylinder, then whatever resolves a singularity has to conserve energy and angular momentum and all the usual conserved quantities, because that's true of the CFT.